Okay, in this video we are going to prove the statement a graph G has a cycle decomposition if and only if all the vertices of G have even degree. So let's look into one or two examples before proving this statement. So let's consider this graph G and let's look into the degree of each vertex here. So the degree of this vertex is 2 and the degree of this vertex is 6, and we can see that the degree of this is 2, 4, 2, 2, 2, etc., etc. So if we look into this particular graph, we can see that the degree of all the vertices is even, and if we believe in this statement, that says definitely this graph has a cycle decomposition. Okay, so let's go and find a cycle decomposition of this graph. Okay, so let's consider this cycle first. Okay, so there we have this C5. Okay, so C5 is this cycle on 5 vertices. Okay, and here we have a triangle here, so that is another member of this family. So we have this C3. Okay, so let's look into this portion. Okay, so let's consider, say, this cycle 1, 2, 3, 4, 5, 6. Okay, a cycle of 6 vertices. Okay, and remaining thing also, it also form a cycle, right? 1, 2, 3, 4, 5. Okay, so we have one more cycle, C5. Okay, so here we can see that if you take the union of the edge set corresponding to each member of this family, okay, we get the edge set of our original graph G. Okay, so here we have a cycle decomposition. And here one cycle decomposition is this C5, C3, C6 and C5. Okay, you could have many cycle decompositions for this graph. Okay, so this statement says if it has a cycle decomposition, then all the degree have even degree. Okay, in this case we saw the other way, all the vertices have even degree. Then definitely, if you believe in this statement, that says this graph has a cycle decomposition, and one such cycle decomposition looks something like this. Okay, you could have many different cycle decomposition. Okay, at least one cycle decomposition exists. Okay, so let's consider another graph which looks something like this. Okay, let that graph be G1. So here we can see that no cycle decomposition for this graph exists, right? What we could do is we could put this into the family and this into a family, and we are left with this edge, right? So that edge, it doesn't correspond to a cycle, that's a path. Okay, that's a path subgraph of this graph. Okay, so that says for this graph we can see that no cycle decomposition exists. And again, if you look into the degree of each vertex here, degree is 2 here, 2 here, 2. Okay, so here we have a vertex of degree 3. So similarly, there is one more, right? 3 and 2 and 2. Okay, so it seems like if a vertex of a particular as a vertex, okay, if the degree of a vertex is odd in a graph, then it has no cycle decomposition kind of thing, right? Okay, so let's go and prove this statement. Okay, so here we can see that if you look into the statement, it is an if and only if statement, so we need to prove two directions. okay, forward direction and the backward direction. Okay, so one direction reads something like this: if a graph G has a cycle decomposition, then all the vertices of G have even degree. Okay, so that's one direction, and the other direction is if all the vertices of G have even degree, then G has a cycle decomposition. So let's go and prove both directions one by one. Okay, so let's prove this direction, that is, if a graph G has a cycle decomposition, then all the vertices of G have even degree. Okay, so here we assume that G has a cycle decomposition, and using that assumption we prove all the vertices of G have even degree. Okay, so suppose that a cycle decomposition of G exists. Okay, then take an arbitrary vertex. Okay, take an arbitrary vertex in the graph G. Okay, then we can see that, okay, here this graph could be disconnected, or maybe some of the vertices may be isolated. Okay, so this two things can happen here: either this vertex B is isolated, okay, that is the degree of V in G equal to 0. Okay, in that case the degree is 0, that 0 is even. Okay, or okay, if the degree of V is not equal to 0, then okay, that V must appear in at least one cycle. Okay, we are assuming that a cycle decomposition of G exists. Okay, or this arbitrary vertex B, it belongs to some number of okay, it must belong to at least one, to some number of cycles in the decomposition. And let that number be, okay, so let that number be, let it be K. So that says this V belongs to K cycles in the decomposition. Okay, so suppose that this K equal to 2, that means this V belongs to, okay, this V, it belongs to 2 cycles in this decomposition. Okay, so in the first cycle it come through a particular vertex and it exit through a different vertex, right? So we can see that degree is 2 in this case, and if V is a part of a second cycle, then again we can see that the vertex V must be entered through a different edge other than these two, and it must leave through a different edge. Okay, if K is equal to 2, in this case we can see that the degree of V is 4. Similarly, if suppose that this V belongs to 3 cycles, again the same kind of argument says, okay, it must enter V through a different edge but exit through a different edge. Okay, in that case we can see that the degree must be, okay, degree is 6. Okay, so it seems like the degree is something like 2k. Okay, and 2k is even. Okay, and that's what we are trying to prove here, right? So if this is the case, then we can see that then this degree of this vertex in this graph G is 2k. Okay, so this is for an arbitrary vertex. We can see that this argument holds for every other vertex in the graph. Okay, then we can very easily see for all vertices in the graph, okay, degree of V in G is even. Okay, and that's what we want to prove. Okay, and we are done with the proof for this direction. Okay, so we suppose a cycle decomposition of G is there. Okay, then we pick an arbitrary vertex v. So we consider two cases here. Either v is isolated. In that case, degree of v is 0. Okay, 0 is even. Otherwise, v belongs to some number of cycles in the decomposition, and let this v belongs to k cycles in this decomposition. Okay, so in that case, we can see that okay, if we consider the first cycle, then it will enter the v through an edge and it will exit through another edge. Okay, and similarly for the second one, it must exit enter and exit through two different edges, because we are dealing with what is called a cycle graph decomposition, and in the graph decomposition the edges are disjoint. Okay, and that says if this v belongs to k cycles, then the degree of v equal to 2k. Okay, and here this 2k is nothing but it's an even number, and this is true for all vertices in the graph. Okay, so for all vertices element of in the vertex set of G, degree of v is even. Okay, so we proved this direction. If G has a cycle decomposition, then all the vertices of G have even degree. Okay, so let's go and prove the other direction. So this direction reads as follows: if all the vertices of G have even degree, then G has a cycle decomposition. So we are going to prove this direction by using mathematical induction, like a strong form of mathematical induction. So proof by mathematical induction on the number of edges. Okay, so here we are going to prove by mathematical induction, and we are going to use a variant called the strong form of mathematical induction, and the induction is on the number of edges in the graph. Okay, so let's consider the basis case. So the basis case is when the number of edges is 0. Okay, if the number of edges is 0, okay, if the number of edges is 0, we have a graph with only isolated vertices which looks something like this. Okay, in this case we have our trivial decomposition in the empty set. Okay, so here the family, the cycle decomposition, it consists of only the empty set. Okay, here we have our trivial cycle decomposition. Okay, so let's state our induction hypothesis, and using that hypothesis, okay, we will prove the general case. Okay, so let me state the inductive hypothesis. Okay, suppose that okay, so we assume that the statement holds for all graphs. Okay, all graphs means all graphs having graphs in which all the vertices have even degree and less than m edges. Okay, so we assume that for all graphs with less than m edges, the statement holds, and we prove for graph with m edges using this assumption. Okay, so our induction hypothesis is, suppose that for all graphs having degree of all vertices all vertices even. Okay, suppose that for all graphs having degree of all vertices even on less than m edges, there exists a cycle decomposition. Okay, so here our induction hypothesis says we are assuming that for all graphs, okay, in which all the vertices have even degree and less than m edges, there exists a cycle decomposition. Okay, and using the assumption we are going to prove that, okay, for all graphs having the degree of all vertices even and m vertices, okay, and m edges, there exists a cycle decomposition. Okay, that's what we are going to do. So our induction hypothesis is about that for all graphs having degree of all vertices even on less than m edges, there exists a cycle. So, okay, using the assumption we are going to prove that for graphs with m edges, okay, the statement holds. Okay. Okay, so let's take a graph G, okay, and the degree of all vertices in G is even, okay, and the number of edges in this graph G is m. Okay, so using the induction hypothesis we are going to prove that, okay, the statement says if all the vertices of G have even degree, then the graph has a cycle decomposition. Okay, so using this induction hypothesis, assuming induction hypothesis, we are going to prove that, okay, that statement it holds true for a graph with m vertices satisfying these conditions, or degree of all vertices is even, and the cardinality of that set or the number of edges is m. Okay, so here this is just an arbitrary graph. The graph, it could be a connected one or a disconnected one. So if it is a disconnected one, then it could have isolated vertices. Okay, maybe something like this. It has some number of isolated vertices, something like this. Okay, then it have these connected components. Okay, and in these connected components, the degree of all the vertices is even. Okay, and that's what our assumption, right? Having all vertices even degree. Okay, so one connected component, it could have many connected components, maybe something like this. Okay, but the thing is that the degree of all the vertices here is always even. Okay, it may be something like this. Okay, and it could have these isolated vertices where the degree of each vertex is 0, and in another component, the thing is that all the vertices have even degree. In another component, all the vertices have degree 3. Suppose that this graph G is something like this. Okay, and next what we are going to do is we are going to isolate all these isolated vertices and only going to consider, okay, these vertices. Okay, so let me define a set X. So the X is going to be the set of all the vertices in G with degree strictly greater than 0. Okay, so what we are doing is we are going to isolate all these isolated vertices, okay, having degree equal to 0. Okay, so this X contains all these vertices, okay, belong to this component and this component. So we are not going to consider these vertices here. Okay, and let's consider a subgraph of this original graph G, and this graph G is there. It's an induced subgraph on this vertex set X. Okay, so that means, okay, here we are considering only this subgraph, and we are calling this subgraph H. So H is nothing but the induced subgraph. Okay, induced subgraph is represented like this, right? Okay, within square brackets. So this is nothing but the induced subgraph of G on vertex set X. Okay, and here again we can see that all the vertices in H have even degree. Okay, so that's how we took this graph G. All the vertices in G is even, and we removed these vertices have degree 0. Okay, and what still remain will have even degree. Okay, so all the vertices in H have even degree. Okay, and also we can see that in H all the vertices have degree greater than or equal to 2, because all the degrees, all the vertices in G have even degree, and we excluded all the vertices having degree 0. Okay, and the next lowest value is 2, which is even, right? 0, 2, 4. Okay, so all the vertices in H have even degree, and that says in H all the vertices have degree greater than or equal to 2. Okay, we already proved a theorem that says if the degree of all the vertices is at least 2, then definitely that graph has a cycle. Okay, so the proof is given in video number 11. Okay, degree greater than or equal to 2 implies a cycle. Okay, so to see the proof, look into video 11, okay, of this playlist. Okay, so that says this graph H, it has a cycle. Okay, so by the video 11, which says degree greater than or equal to 2 implies a cycle. Okay, we can say that there is a cycle in H. Okay, and let's call that cycle C. Okay, next what we are going to do is we are going to build a new graph. Okay, G dash, and G dash is obtained by taking our G and taking away all the edges, okay, belonging to this cycle C. Okay, now we have a new graph. Okay, what we did is, okay, we took this graph cycle C. Okay, such a cycle exists because in H all the vertices have degree greater than or equal to, and okay, using the theorem that we proved in video number 11. Okay, so since there is cycle H and we called it C, okay, we build a new graph G dash by taking away all the edges belonging to this cycle. Okay, and here we can see that first of all G dash has less than m, okay, less than m vertices, okay, less than m vertices, and Okay, G dash has less than m vertices and all the vertices have degree even. Okay, so here what we did is we took this cycle, okay, cycle C, and we took away all the edges from this graph and we built this graph G dash, right? Okay, so suppose that this is a part of, okay, if we consider this particular vertex, we can see that we took away two edges, right? Okay, or maybe multiple of 2. Okay, so if you subtract a multiple of 2 from something even, again you will get some even quantity, right? Okay, so that says, okay, anyway we are removing something from G, so G dash has less than, that's also very important here, less than m not vertices, okay, less than m edges, okay, because we removed this cycle. So for cycle to occur, okay, we need to have this kind of structure, okay, at least we removed a triangle, okay, so we removed at least, okay, 3 edges, right? So that says G dash definitely has less than m edges and all the vertices have degree even, okay, because when you remove a particular cycle, okay, we are removing 2 edges instead of a particular vertex. So if this vertex started with an even number of degree, okay, started with an even degree, and if you remove a multiple of 2 from that even, because still the degree of this vertex is even, okay, and that says all the vertices have also degree even. Okay, now what we can do is we can invoke our induction hypothesis. So all the vertices are even and we have a graph with less than m edges, okay, so here G dash has less than m edges and all the vertices have degree even, okay, and by our inductive hypothesis, so by inductive hypothesis we can very easily see that this G hash, okay, this graph G dash has a cycle decomposition. Okay, and call that cycle decomposition say C dash, okay, so that's by our induction hypothesis. So we assume something like this, okay, for all graphs having degree of all vertices even and less than m edges, okay, there exists a cycle decomposition, okay. So now what we build is, what we did is we built this graph G dash and G dash has less than m edges and all the vertices have degree even. So by induction hypothesis G dash has a cycle decomposition, let's call it, okay, C dash, okay. Now we have this C and this C dash, okay, C dash, okay, C is just a cycle and here this C dash, okay, it is a family of cycles, okay. C dash corresponds to a cycle decomposition for m, okay. Okay, what we are going to do is we are going to use this C and C dash, okay. Now we can see that, okay, we can build a cycle decomposition for our graph G. So we started with this graph G, right? Okay, now we can find a cycle decomposition of that graph, okay. Let that family be F and this F is nothing but take this cycle C and this cycle decomposition and the union of these two, okay. So this is, okay, this set is nothing but, okay, it is a cycle decomposition of the original graph, G, okay. So that's it. So we proved the other direction also, okay. So we proved both directions. So here we used a strong form of mathematical induction, and the induction is on the number of edges. Okay, so basis case, if the number of edges is 0, okay, we have this graph. Okay, a graph with no edges. In that case, we have this trivial cycle decomposition. Okay, so in order to prove the general case, we set up this inductive hypothesis. So we suppose that for all graphs having degree of all vertices even and less than m edges, there exists a cycle decomposition. Okay, then what we did is we took a graph G satisfying these two conditions. All vertices have even degree and the number of edges is m. Okay, and we isolated the isolated vertices and we build this set X, the set of all vertices with degree greater than 0, and we consider this subgraph H. Okay, if we look into this graph subgraph H, we can see that all the vertices have degree greater than or equal to 2 because we isolated all the vertices having degree 0. Okay, now we already proved in video number 11 that okay, if the degree of all the vertices is greater than or equal to 2, then that graph has a cycle. Okay, so we invoke that particular theorem that we proved in video 11. Okay, so that says there is a cycle in that H, and we call that cycle C. Okay, using this cycle C, okay, we build a new graph G dash by taking away all the edges belonging to this cycle C. Okay, now we can see that G dash has strictly less than m edges and all the vertices have even degree. Okay, even though if you take a cycle, okay, so we remove two edges and we started with a vertex of degree even and we remove multiples of 2. Okay, so we can see that the degree still remains even, right? Okay, so all the vertices have degree even. So now we can invoke our induction hypothesis. So by induction hypothesis, this graph G dash has a cycle decomposition, and let's call it C dash. Okay, so C dash is a family of cycles. Okay, now what we do is we will go back and build the cycle decomposition for our original graph. Okay, so for our original graph, the family contains this cycle with that cycle union the cycle decomposition C dash for G dash. So this F is a cycle decomposition of the original graph. Okay, so that's it, and we are done with the proof for this statement. Okay, so a graph has a cycle decomposition if and only if all the vertices of G have even degree.